Welcome friends, Igor is here, and in this video we will talk about the kernel of a linear transformation. In this lesson we will define the kernel of a linear transformation, compute the kernel of one sample linear transformation, prove that the kernel of a linear transformation is a subspace, and show that a linear transformation is injective if and only if its kernel is trivial. Let's get started. First, let's discuss the notion of a preimage of a function. The defining property of a function is that for each input there is exactly one output. However, given an output of a function, there could be more than one input that generate that same output. And the collection of all the inputs that generate the given output is called the preimage. Suppose we have a linear transformation T from the vector space U to the vector space V. The preimage of the vector V is the set of all vectors U in the vector space U such that T of U is equal to the given vector V. So in essence, the preimage of a vector V consists of all those inputs of the transformation T that give that one prescribed output. Notice that the notation for the preimage is similar to the notation of the inverse function. This is because when a function is invertible, then to compute the preimage, you just need to compute the value of the inverse function. But the notion of the preimage makes sense even for non-invertible functions. And now we are ready to define the notion of the kernel of a linear transformation. Informally speaking, the kernel is a subset of the domain of the linear transformation, which consists of those vectors that get sent to the zero vector. And here is a formal definition of the kernel. Notice that the kernel of a linear transformation is always a subset of the domain. Recalling the definition of the preimage, we can say that the kernel of a linear transformation is the preimage of the zero vector. Let's compute the kernel of this linear transformation T that goes from C3 into C5. We're looking for all possible vectors U in the domain C3 such that T of U is the zero vector. And so we explicitly write out this vector equation. This vector equality is equivalent to a homogeneous linear system in 5 equations and 3 unknowns. We find the reduced row echelon form of the coefficient matrix of this linear system, and we notice that the third variable is a free variable. The kernel of T is the solution set of that homogeneous linear system, therefore it is infinite, and it can be described as a span of a set which consists of a single vector. But we also know that spans are subspaces. So in this case, this kernel is in fact a subspace of the domain. Is it always going to be the case? The answer is yes. The kernel of any linear transformation is always a subspace of the domain. Let's apply our 3-part test for a subspace. First, is this set non-empty? Yes, because every linear transformation sends zero vector to the zero vector. Therefore, the zero vector of the domain is always a member of the kernel. Second, is this set closed under vector addition? Let's take two vectors x and y in the kernel of T. Then, let's see what happens when we apply T to the vector x plus y. As a linear transformation, T respects vector addition. Also, x is a vector in the kernel of T and y is a vector in the kernel of T. Therefore, T of x is the zero vector and T of y is the zero vector. But zero vector plus zero vector is the zero vector. This computation shows that the value of T at the vector x plus y is the zero vector, and this means that x plus y is a vector in the kernel of T. Therefore, the kernel is indeed closed under vector addition. Third, is it closed under scalar multiplication? Let's take any vector x in the kernel of T and an arbitrary scalar alpha. Then we are going to apply the linear transformation T to the scalar multiple of the vector x by the scalar alpha. T is a linear transformation, therefore we can factor the scalar alpha. x is a vector from the kernel of t, therefore t of x is the zero vector, and the scalar multiple of the zero vector by any scalar is still the zero vector. This computation shows that the value of t at alpha x is the zero vector, and therefore alpha x is a vector in the kernel of t. This shows that the kernel of t is closed under scalar multiplication, and this completes the proof that the kernel is a subspace. So the kernel of a linear transformation is the preimage of the zero vector. The following result says that the preimage of any vector can be obtained by shifting the kernel. This shift is achieved by adding one particular vector from the given preimage. I would like to leave it as an interesting exercise for you to prove this result. This theorem should remind you of the following result we established earlier. All solutions to a given linear system can be obtained by taking one particular solution of this linear system and then adding all possible elements of the null space of the coefficient matrix. You see the analogy here? One particular solution of the linear system corresponds to one particular vector from the given preimage, and the null space of a matrix is the analog of the kernel of the linear transformation. In fact, knowing the kernel of the linear transformation allows you to decide if the linear transformation is injective. It turns out that a linear transformation is injective if and only if its kernel is trivial. That means the kernel contains only the zero vector. This is an if and only if statement, so we are going to establish two separate implications. In the forward direction, we are going to assume that the linear transformation is injective. Then we have to prove that the kernel of t is just the zero vector. We are trying to prove the equality of two sets, and so we will show two set inclusions. First of all, the set which consists of the zero vector is a subset of the kernel of t because we already established today that the zero vector is always a member of the kernel. For the opposite inclusion, let's take an arbitrary vector x in the kernel. Then the value of the linear transformation t at that vector x is the zero vector. But on the other hand, this is also the value of t at the zero vector, because every linear transformation sends zero vector to zero vector. But this equality now says that the value of t at the vector x is the same as the value of t at the zero vector. The linear transformation is injective, so the equality of the values forces the equality of the inputs. This means x must be the zero vector. The only member of the kernel of t is the zero vector, and therefore the two sets are equal. For the opposite implication, let's assume that the kernel of t is trivial, and we have to show that then t is injective. I am going to use the definition of an injective linear transformation in this case. Let's assume that the value of t on the vector x is the same as the value of t on the vector y. Then the value of t on the vector x minus y is t of x minus t of y. This is because t is a linear transformation. But here we are taking the difference of two identical vectors, so this difference is the zero vector. This computation shows that the value of t on the vector x minus y is the zero vector, and this means that the vector x minus y is a member of the kernel. But we assumed that the only vector in the kernel is the zero vector, therefore x minus y is the zero vector. This means x is equal to y, and we have verified that t is an injective linear transformation, because the equality t of x equals t of y forced the equality x equals y. Let me put this result in the context for you. Saying that the kernel of t is trivial is actually saying the following. The only way to get the zero vector as a value of the linear transformation is to use the zero vector as an input. In other words, distinct inputs cannot go to the same value as long as that value is the zero vector. But now, knowing just this, knowing this property only for the zero vector allows us to say that this property actually holds for all vectors. If we take now any value of the linear transformation in the codomain, it can be achieved only by a unique input from the domain. Let's revisit our example where we compute the kernel of this given linear transformation. Because the kernel is not trivial, it contains non-zero vector, we can conclude right away that this linear transformation is not injective. If you found this video useful, please give it a like to help others discover this content and subscribe to this channel to see more of these videos. In the next video in this series, we will discover some properties of injective linear transformations. I will see you later.